Section 2.4, Factor and solve polynomial equations in Algebra 2. First, let's look at some general factoring review. We've looked at factoring trinomials before. When we factor trinomials, our goal is to split them up into two binomials. Now, we have to be careful because the product of the binomials, we need to make sure does in fact equal our original trinomial. When I factor trinomials, I think FOIL in reverse. I want first times first to equal first. Well, the only way to get 2x squared is 2x times x. And then I set it up so that last times last equals last. So positive 5, negative 4 would get me to negative 20. But I need to make sure that the outside times outside combined with the inside times inside do in fact equal the middle term here. So I check those, and I look here and I see 2x times negative 4 is negative 8x, and 5x, or 5 times x is 5x. Combine those, and I do get negative 3x. So I can see that that is factored correctly. If I recognize certain patterns, it can save me a little time. If we have a perfect squared trinomial, it'll factor into a binomial squared. Remember what you did in last section. To multiply this out here, we can take the first term and square it, the last term and square it, and then multiply those together and double it, we get the middle term. So going in the reverse order, I can factor this into x plus 4 squared. Or I might have the difference of two squares. If I have the difference of two squares, it's going to factor into that sum and difference pattern. First times first equals 9x squared. Last times last equals negative 1. And the outside times outside plus inside times inside would be opposites of each other. And so then there would be no x term in my original. So that's how I can quickly factor the difference of two squares. Where I want to start anytime I factor is actually right here. Always look first if there's any common monomial factor to factor out. In this example, looking at my terms, 8x squared and 20x, I would see they both have a common factor of 4 and they have a common factor of x. So I can factor out 4x from both terms. Now keep in mind, however I factor it needs to be equivalent to what I started out with. So when I factor out the 4x from the 8x squared, I would be left with 2x because 4x times 2x does equal 8x squared. And when I factor out the 4x from 20x, I'd be left with positive 5. I can always check my work by mentally distributing the 4x back through and check and make sure it does equal what we started out with. If I'm asked to factor something completely, it means writing the polynomial as the product of unfactorable polynomials with integer coefficients. So I want to keep breaking up the polynomial into things I can multiply together that still equal the original polynomial, but to the point where they can't be split up any further. Now, we're reviewing polynomials and factoring because we will apply it in multiple ways to come. Let's work through a few examples. I always want to start with taking out the greatest common factor if there is one. So I always look at all the terms first. And I can see that all of all my terms here have a y in them. Now for the numbers, because I start with 1y cubed, it's not divisible by 4 or negative 12, so I don't have any numbers to factor out, but I definitely want to factor out a y from all three terms. When I factor out a y, I'd be left with y squared minus 4y minus 12. Now, sometimes that's all I'll be able to do, but I always want to see if I can factor further what I have left. The y is going to stay in front. It does not disappear. I don't want to multiply it back in. But I do want to try to split up that trinomial into the product of two binomials. I know that first times first needs to equal y squared, so I'm going to need y and y. Last times last means equal -12. Now I have some options there. I do know I'm going to need a positive and a negative. And then I have 3 times 4, or 2 times 6, or 1 times 12. But I need the right combination that will also get me to -4y in the middle. So think about it. If I multiply outside times outside, combine it with inside times inside, that's where the -4y comes from. So if I think about 3 and 4, well, there's no way that I can have a 3y and a 4y and get to -4y. So then I'm going to think about 2 and 6. Well, if I make the 6 negative and the 2 positive, then that would give me a -6y when I do outside times outside, and a positive 2y when I do inside times inside. Add those together, I get -4y. You can see I found the right combination that equals my original polynomial, but is now factored completely. So I would write my answer as y times y plus 2 times y minus 6. Now on to example B. Once again, looking at all my terms, I can see that they're all divisible by 3 and also by x. So that means I want to factor out 3x from all 3 terms. So 3x divided out of 3x squared, I'd be left with, 3x cubed, I'd be left with x squared. Then 30x squared divided by 3x would be 10x. And 75x divided by 3x would be 25. So keep in mind, each step I do remains equivalent to what I started out with. If I were to distribute the 3x back to all 3 terms, it would equal what the original polynomial is. Now, I need to keep going if possible. 3x will stay out in front. Let's see if we can split up this into 2 factors. And I can see I'm going to need x times x to get x squared. Since this is positive and this is positive, I'm going to have plus and plus. And then to get to 25, 5 times 5 would equal 25. And checking outside times outside plus inside times inside, 5x plus another 5x does get me to my middle term of 10x. So my answer I can write as 3x times x plus 5 squared. Now you might have noticed this as being a perfect square trinomial and could have skipped this work and gone straight to writing it as a binomial squared. Our polynomial is now factored completely, and that is our answer. Looking at our next example, what would you factor out? Well, I see 5 goes into 5 and 80, so I can factor out a 5. And I see that g cubed would go into g to the 5th power and into g cubed. So I can factor out the greatest monomial factor of 5g to the 3rd power. Then I'd be left with, in parentheses, g squared minus, 80 divided by 5 would be 16. And I don't have any g's there because I factored them all out. Now, let's see if we can factor this any further. I notice that this would be the difference of perfect squares. So that factors into g plus 4 times g minus 4. Because, once again, first times first would equal first. Last times last would equal last. And the outside times outside plus inside times inside are opposites. They cancel each other, thus leaving no g term in here. So my polynomial is now factored completely, is equivalent to what we started out with, and that is my answer. Now here's a pattern you might not have seen before. If we have the sum of 2 cubes, now what we'll be looking for here is something like 8x to the third power. That would be a perfect cube because the cubed root of 8x to the third power is just 2x, because 2x times 2x times 2x would equal 8x cubed. Or something like 27y to the third power. Well, I could rewrite that as 3 times y raised to the third power, so that would be a perfect cube. So if I have something like that, and I'm adding them together, I can factor it into this binomial times this trinomial. Let's look at the pattern. If we take the cubed root of my first term and add it to the cubed root of the second term, that's the first part of my factors, is the sum of those two. Then I want to square the a minus the product of a times b plus b squared. In our example here, I first would identify a to be 2x, because 2x times 2x times 2x equals 8x cubed. And then I would identify b to equal the cubed root of 27, which is 3, because 3 times 3 times 3 equals 27. Then I can follow the pattern and write it as a plus b, 2x plus 3, times a squared, 2x times 2x will be 4x squared, minus a times b, so 3 times 2x, which is minus 6x, and then plus b squared, which 3 squared would equal 9. That is now factored completely. The way this pattern works is that this trinomial here, I don't need to try to factor any further because it won't be factorable any further from there. Unless I forgot to take out a greatest common factor earlier, then I might still need to do that. The difference of two cubes then, if it's the difference, follows the same pattern, just our signs are opposite, well, almost opposite. Instead of a plus b, we end up with a minus b. And then we have a squared plus ab plus b squared. So notice this pattern goes minus, plus, plus, versus up here it goes plus, minus, minus. Go ahead and check out this example. 64x cubed minus 1. We want to recognize that this is a perfect cube because 4x to the third power equals 64x cubed. 1 is also a perfect cube because 1 cubed equals 1. So when I factor it, I take, once again, a minus b, so 4x minus 1, times the first term squared, which is 16x squared, plus 4x times 1, which is just plus 4x, and then plus b squared, which would just be plus 1. And that is now factored completely. We'll do some more examples. So I'm asked to factor this completely. The first thing I want to look for is there a greatest common factor to factor out of both terms? And for a, I don't see any. 27 and 125 do not share any common factors. Then I want to look for any special patterns I see. And here I notice I have the sum of perfect cubes. The cubed root of 27 is 3. Cubed root of x cubed is x. So anytime I have an x cubed, I want to think about, is it the sum or difference of perfect cubes? Then the cubed root of 125 is 5, because 5 times 5 times 5 is 125. So now I can follow the pattern. This will always factor into the binomial times the trinomial. And the binomial is the cubed root of the first term, so in this case 3x, plus the cubed root of the second term, which is 5. Then in my trinomial, I want to square the first, or square what a is, so 3x times 3x, 9x squared, minus 3x times 5, which is 15x, plus b squared, so plus 25. That is now factored completely. And go ahead and try multiplying it out to check. if you multiply out 9x squared minus 15x plus 25 times 3x plus 5, we should in fact get 27x cubed plus 125. Go ahead and try that. Let's look at another example. Once again, look at the terms you have first. Is there a greatest common factor to factor out? Well, here I can see both my numbers, -2 and 250, are even, so they're divisible by 2. I also see that I have at least a d squared in both terms, so I can factor out d squared from both of them. Now, I prefer to start with a positive leading coefficient, so I'm not just going to factor out a 2, I'm going to factor out a -2 and d squared as well. So then in parentheses, I can be left with positive d to the third power, then minus 250 divided by 2, which is 125. Now let's see if we can factor this further. I still have the minus 2d squared, stay out in front. And now I want to recognize this pattern here is the difference of perfect cubes. I recognize that because the cubed root of d cubed is just d, and the cubed root of 125 is just 5. So I can factor that into the binomial times the trinomial. And remember, if I look at the first term here, the cubed root of it, which is just d, is what a equals. Then because this is subtraction, it's going to be minus the cubed root of 125, which is 5. Then for the trinomial, I want to take what a is and square it, so d squared. Then I want to multiply this times this together, and I get plus 5d. And remember, with the subtraction, it's going to go minus, plus, plus, following our pattern. So this 5 I'm going to treat as a positive because the negative has already been taken care of within the pattern. And then last times last, so we want to square the b here, and I get plus 25 in parentheses. So my answer, this problem completely factored, is that right there. You might remember factoring 4-term polynomials from Algebra 1. With 4-term polynomials, we want to try a process called grouping. If my goal is to factor something with 4 terms, I'm going to group the first 2 terms together, group the second 2 terms together, and put a plus sign, whoops, it's a little off here, a plus sign in between. Now notice this is addition here, so it's not, they aren't factors, we're not to multiplication yet, but what I can do now is look at the first group. I want to look for common factors and factor those out. Now both of these terms have an they both have an r. So I can factor out r from both terms, which is what they did right here. And we factor out r, we're left with a plus b. And then for my second group, they have a common factor of s. So we can factor out s, and we're left with, once again, a plus b. Now, notice what we have here is we have a common binomial factor in both my groups, a plus b and a plus b, which allows me to factor out that common binomial factor. Remember, if I factor out something, I put it out in front, and then I show what I'm left with. So factoring out a plus b from the first group, I'm left with r. Factoring out a plus b from the second group, I'm left with s. So I have a plus b times r plus s are the factors of that 4-term polynomial. Now let's look at a more specific example. If my goal is to factor this 4-term polynomial, once again, the first thing I'm going to do is I'm going to break it into groups. I'm going to put the first 2 terms together, a plus sign, followed by the second 2 terms. Now, I don't want to put a minus sign in front of the parentheses because that would change the sign of both of these terms, and it's easy to make a mistake with that. So, if I'm consistent and just start with a plus sign in between, then I can continue with the negative in parentheses, minus 3t minus 5, and it still is equivalent to what I started out with. Now again, my goal is factoring here, so we need to continue. Let's look at my first group. What's the greatest common factor between 27 and 45? Well, 9 goes into both of those. What about for t cubed and t squared? Well, t squared goes into both of those. So I can factor out 9t squared from both my terms. Dividing 9t squared out of the first term, I'm left with 3t. Dividing 9t squared out of the second term, I'm left with a positive 5. Now let's look at the second group. At first glance, I can see they both don't have any common factors. 3 and 5 don't anyway. There's not more than one t in there. But I do see they're both negative. And because I want this to factor into something that has 3t plus 5, I do want to factor out a negative 1, which will change my factor into 3t plus 5. Now, I have to have a common binomial factor to continue from here. If this was not the same as this, then either I did something wrong or it's not going to be factorable in this way. Because now I want to factor out that common binomial factor, 3t plus 5. And when I divide it out of the first group, I'm left with just 9t squared. And when I divide it out of the second group, I'm left with minus 1. Now, it feels like we should be finished, but we're not quite yet. 3t plus 5, I cannot factor that any further, so that's finished. However, 9t squared minus 1, I can factor further. I want to recognize that that is the difference of perfect squares, so it can factor into that sum and difference pattern. So, let's come up here where I have some space, and 3t plus 5, I want to make sure that I rewrite that. It's still there. And then the 9t squared minus 1, I can split up into 3t plus 1 times 3t minus 1. And that is our answer. Let's practice some more factoring. If I want to factor completely 10x to the fourth minus 10, the first thing again I want to look for is the greatest common factor to factor out. Well, I have 10 in both terms, so I can definitely factor out 10, but that looks like it. Now when I factor out 10, that would give me x to the fourth minus 1. Now a lot of times I see people leave out this minus 1, but keep in mind, negative 10 divided by 10 does equal 1. And if I leave that out, then it doesn't stay equivalent to what I started out with. Notice if I distribute the 10 to check my work, it does equal 10x to the fourth minus 10. Now I want to keep going if possible. 10s will stay out in front, and then I can notice that this is the difference of perfect squares. I can split it up into x squared plus 1 times x squared minus 1. Because x squared times x squared does equal x to the fourth. Positive 1 times negative 1 does equal negative 1. And again, the outside times outside plus inside times inside would be opposites and cancel. Now, I can still go yet further with this. The x squared plus 1 is not the difference of perfect squares. And because it's actually the sum, we can't split it up any further. However, x squared minus 1 is the difference of perfect squares, so I can factor it into x plus 1 times x minus 1, the sum and difference pattern. It doesn't work for addition, because we need a positive times a negative to equal a negative, and those have to be opposites in order to get the outside times outside plus inside times inside to cancel. That wouldn't happen if I tried to make them both positive. All right, so that's factored completely, and there's my answer. Let's look at the next example. First of all, 3, 54, 51. Looks like they're all divisible by 3. M to the 12th, m to the 7th, m squared, those would all be divisible by m squared. So let's factor that out. And when I divide out 3m squared, I'd be left with m to the 10th power plus, let's see, 54 divided by 3 is 18. So I'd have 18 m to the 5th power. Then 51 divided by 3 is 17. And now I have a trinomial that I want to see if I can factor further into a binomial times a binomial. Now I can use properties of exponents that we've been looking at to split up m to the 5th power. Remember, when I multiply like bases, I add the exponents. Now, because this is m to the 5th in here, I do want to split m to the 10th up into m to the 5th and m to the 5th. Because m to the 5th times m to the 5th would equal m to the 10th. And then when I do outside times outside plus inside times inside, I will get m to the 5th as well. Then I want to look at the signs. Both being positive mean that I'm only dealing with positive numbers, and I can make those both addition. Last times last equals 17. Well, the only thing I can multiply that are whole numbers to get 17 would be 17 and 1. So let's see if that works. So I set it up so that first times first equals first. I set it up so that last times last equals last. And now I'm going to check outside times outside would be 1m to the 5th power plus inside times inside, 17m to the 5th power. Well, 17 plus 1 does equal 18m to the 5th. Now I want to see if I can factor any of these further. Well, this is not the sum of perfect cubes, nor the difference of perfect squares. So neither of these can I factor any further. There's my answer, and my polynomial is factored completely. We can use factoring to solve equations. The first thing I want to do is get my equation set equal to 0. So I'm going to bring everything to the left side. I would need to subtract 12x cubed and add 16x to leave me with nothing on the right side and move everything to the left side. Now, I want it set equal to 0 because if I'm able to factor it into multiple factors, a, b, c, and if the product of those equals 0, well, that means that either a has to equal 0, b has to equal 0, or c has to equal 0. That's called the zero product property, and that's the property I'm going to apply here. So once I have it set equal to 0, I want to factor it so that I have a product and then can set each factor equal to 0 and solve for x. So factoring, I'll first look at all my terms. I see they're all even, so I can factor out a 2. I see they all have an x in them, so I can factor out an x. When I factor out 2x, I would have then x to the 4th minus 6x squared plus 8. And as I factor, I always like to do a mental check and distribute, make sure it does equal what I started out with. Now I want to keep factoring until I can't factor any further. I have a trinomial, so I'm going to try to split it up into the product of two binomials. Because I have x to the fourth here and x squared here, I know I want to split this up then into x squared times x squared, because x squared times x squared would equal x to the fourth. Then I'm going to look at the signs. I see I have a positive here and a negative here. Well, if last times last is equal a positive, but then outside times outside plus inside times inside needs to equal a negative, that tells me these both need to be negative, because a negative times a negative will get me to a positive, but a negative plus a negative will get me to a negative. For 8, I could split it up into 2 times 4 or 1 times 8, but I want to get to minus 6x squared. So I can see that if I make it a 2 and a 4, that 4 times x squared plus negative 2 times x squared would get me to negative 6x squared. Now let's see if we can factor these any further. 2x is factored completely. X squared minus 2 is the difference of a perfect square and a not perfect square. So because 2 is not a perfect square, I can't factor that any further. We'll leave it x squared minus 2. However, x squared minus 4 is the difference of perfect squares, so I can factor it into the sum and difference pattern of x plus 2, x minus 2. Now that's factored completely, I see I have 4 different factors. If any of those factors equals 0, the product will equal 0. So to solve, I want to set each factor equal to 0. So 2x could equal 0, which would mean that x equals 0 is one of my solutions, because 0 divided by 2 is just 0. Next factor, x squared minus 2 could equal 0. To solve this for x, let's see, we can add 2 to both sides. So I have x squared equals 2. Then taking the square root, I would have x equals positive negative square root of 2. Remember that when we take the square root, we have to put the negative back in, because a negative times a negative still equals a positive. So that actually gives me 2 more solutions. And then I have x plus 2. If that equals 0, then x would equal negative 2. And my last factor of x minus 2, set that equal to 0. So then x would equal positive 2. So we have one solution, a second solution, a third and fourth solution. Whoops, let me circle that. Third and fourth because of positive, negative. And then over here, a fifth solution of 0. So you can see with high degree polynomials, like to the 5th power, we can end up with quite a few solutions. What those solutions mean is if I plug them back in here for x, this left side will equal the right side. Let's look at one more example. Suppose you're making a metal tray by cutting equal squares from each corner of a rectangular sheet of metal that is 12 by 16. What should the dimensions of each cutout square be for a volume of the tray to be 60 cubic inches? Let's see, this must be 12 inches by 16 inches because we are dealing with cubic inches down here. Now, where I would start is just by getting a visual of what we're talking about here. So we're starting out with a rectangular sheet of metal that's 16 inches by 12 inches. Then we're cutting out squares from each corner. Now, we don't know how big those squares are, so I'm going to label that x. So each of those being x units by x units. Now, imagine folding up, cutting out those squares, and then folding up each side along that dashed line to form an open box. Well, a volume of a box is length times width times height. And we know our volume needs to be 60 cubic inches. Well, let's look at our length. The length of our box would be from here to here. So that would be the total length of 16 inches minus what I'm cutting out from this side and this side. Well, that would be x from this side and x from that side. So we have 16 minus 2x. Then the width of the rectangle started out as 12 inches, but we're taking away x from both sides as well, so 12 minus 2x would be our width. And then the height is just going to be x, because that's the amount that we're folding it up. So I have a volume equation of length, 16 minus 2x, times width, which is 12 minus 2x, times the height, which is x, and I want that to equal 60. Now, the left side is factored, but it's not set equal to 0. So what I'm going to have to do is multiply out the left side, bring the 60 over so it is then set equal to 0, and then I can factor and solve. Now, a problem like this, from this point, guess and check might be the fastest strategy to figure out what x is. I plug in a value of x. If it's below 60, I plug in a larger value of x. If I plug in something and get over 60, well then I make x smaller. But we're practicing factoring here, so let's go ahead and do that method. All right, I rewrote it so I'd have more space. So let's go ahead and multiply these two binomials together. So start out first times first, 16 times 12, which is 192, plus outside times outside, 16 times negative 2x would be minus 32x. Inside times inside, 2x times 12x would be minus 24x. Then last times last, 2x times 2x, and it's a negative times a negative, so that's going to be positive 4x squared. Then this we can simplify, and then we also need to multiply it by x. And keep in mind it still equals 60. So I'm going to both distribute the x and combine like terms in the process. So the 192 times x would be 192x. Negative 32 minus 24 would be a negative 56. And that's x, but then I multiply it by the other x, so that would be the x squared. And then plus 4x times another x would be 4x cubed. And once again, that equals 60. Now, I want to subtract 60 from both sides, and I can see I don't have anything to combine that with on the left side. And then my goal is going to be to factor it. Now, I'm going to have 4 terms, so I want to try factoring it by grouping. And if I'm factoring it by grouping, I do want to start with the highest exponent first. I want to write in standard form. So when I rewrite this, I'm going to do 4x cubed, then minus 56x squared, then down to the 192x, then minus 60 that I subtracted from the right side, and now it's set equal to 0. 4 terms, let's try factoring by grouping. Group the first 2 terms together, leave a plus sign in between, group the second 2 terms together, and now I want to look for greatest common factors. In the first group, 4 and 56 are both divisible by 4. And I could also factor out x squared, which would leave me with x minus